we want to take a look at our K. When we look at our K value, you see this is 10 to the minus 31. 10 to the minus 31 is going to heavily bias the reactants. And if we have a lot of product here and the reactants are heavily biased, there's going to be a big change. We're going to have to lose a lot of this product. If the K is very big, then it's going to heavily bias the products. And so one of the tricks that we do is we take a look at if one side is favored over the other, largely. And then we do something called resetting the initial conditions. And so let me talk about that now. These reactions can go either way. It's like a seesaw. So if the seesaw is too far one way, it's going to change and achieve the balance. So let's say we have the seesaw tilted too far to the left. And this is the center point here. Eventually it's going to reach equilibrium. Equilibrium is both sides weigh the same amount. It'll end up here. But let's say if the seesaw were too far right, would we achieve the same equilibrium? Yeah, it's gonna just reach the same equilibrium. Nothing's changed, right? And so when we are approaching equilibrium, we can either approach it from the left or we can approach it from the right. It doesn't really matter which way we go. Or it could be biased slightly one way or the other, but we're going to get it. And so what we do here is we just try to make the change as small as possible. So let's look at a water tank analogy. So if the two sides are equivalent, then it's not heavily biased towards one side or the other, And so here it may be useful. It may be useful to reset. To eliminate binomials in the math. The binomials you'll see where those pop up. And so this one's not biased towards one side or the other, but we might reset it regardless. That is, we might put all the water on one side and have no water on the other side. So in this case, the change we're going to have, the water is going to flow this way. Or we could reset all the water to the right and have it change the opposite way. So if this is some kind of water tank that's connected here, it doesn't matter which side we approach equilibrium. So we can approach it from the left side, which will shift it to the right, or we can approach it from the right side, which will shift it to the left, as long as the quantity of water doesn't change. So if I have, let's say I have 100 gallons of water here. I could start with all 100 gallons on the left side or all 100 gallons on the right side. Or I could start with 50 gallons on the left and 50 gallons on the right. This would be 100 gallons total. Now, it makes a difference if one side is heavily biased over the other. So in the previous example, what we saw is that the equilibrium heavily favors the left side here. So in the previous example, I had some water here, but I had water here, and that's going to go way up here because they'll have the same amount of water here. And so this goes way up, and then so what we're going to see is there's going to be a big shift to the left to reach equilibrium. And so if this water just keeps going up, we've got a lot of water to drain out here before it reaches the level. And so in this case, it might be better to reset everything to the left. So if we put everything on the left here and then let it shift right, then over here this is going to be a big change, although this is probably not the most, this would be a small change. And so what we can do is, this is kind of what we were looking at in that one particular problem, but let's take a look at a typical problem. A typical problem, let's say, is going to have a situation like this. Say this is going to be a big K. A big K means all the water wants to be on the right. But we're going to start off with only reactants. If we start off with only reactants, then what's going to happen? Well, there's going to be a big change to the right versus this. So let's say I have 100 gallons here, and then in the end I need 99 gallons on the right and 1 gallon on the left. Or let's say, maybe we'll make it a little bit more extreme. Let's say I need the 99.9 gallons on the right, 99.9 gallons, and then just 0.1 gallons on the left. And so in this type of scenario here, we're going to have 99.9% change. It's a big change. 99.9% of the water is going to shift to the right. So what we do in the calculation is this. We do a reset. And so what a reset is I'm just going to move all the water to the right. Oops. So now I'm going to have 100 gallons over here. And so now I'll do my calculation. So this is calc without reset. The calculation without the reset is going to be a 99% change, 99.9% change. But if I reset, oops, I ran out of room here. If I reset, then we're going to have a small change here. And the small change is just going to be 0.01%. Now, what's the advantage of that? The advantage is probably due to your calculator. At the extremes, your calculator is going to fail. If it were just like this, 99.9 and 0.1, it won't fail. Your calculator will be okay. But at the extreme, let's say I had a 99.99999. Let's say your calculator only holds 10 digits. You can see how many digits your calculator holds by looking at the manual. If your calculator only holds 10 digits, it's incapable of registering this number. And so this number is just going to be 100. % change. And if you have a 100% change, then we're not doing an equilibrium calculation. We're doing a Chem 1A style, either 0% or 100% reaction. And so we need to do an equilibrium style calculation where we can double check our answer. Did I double check the answer? Yeah. Did I double check the answer earlier? So this is why we'll do this. So let's redo that calculation via reset. And so I'll just redo calc with reset. And so I have nitrogen plus the oxygen. This is a two-way reaction. It's going to give me 2 NO gas. Since it can go either way, I can approach equilibrium from the left or from the right. It doesn't really matter. If I take my original initial conditions, I had 1 bar of nitrogen, 1 bar of oxygen, and 1 bar of NO. That's under standard conditions. But what I'm going to do is I'm going to reset this. Now, when I reset, I cannot, create matter, and I cannot destroy matter. And so I have to take all the atoms that were originally there and just reshuffle them. And so what I'm going to do is I'm going to reset this left. When I reset it left, I do this on the reset. I look at the limiting reagent. So over here, going left, I just have NO. That would be my limiting reagent. I'm going to lose all of it. And so this is going to be minus 1 bar or minus, in the reset, let me do it like this. With the reset, I'm going to do it both with just a variable. So this is going to be minus 2, I'm going to call it y. And then over here I'm going to have plus y. And then I'm going to have plus y here. So when I reset it left, I assume 100% reverse reaction. And that depends on the limiting reagent. So assume 100% reverse. So I'm going to move all the atoms to the left. All the atoms that I can move to the left, I'll move to the left. And so this must mean y is 0.5 bar. And so what that's going to do is my reset conditions are now going to be 0 bar, and then I'm going to add a half a bar over here. So this will be 1.5 bar. I'm starting off with exactly 1 bar, so this is why the sig figs I'm ignoring. This is going to be 1.5 bar here. So I still have all the same number of atoms. I just moved all the atoms to the left side. And so like the seesaw, it doesn't really matter as long as everything's there. Okay, now I'm going to do my equilibrium calculation. So there's going to be a change. Now, when I look at this, I have nothing on the right. So the change has got to go to the right. And so this is going to be minus x bar. I'm going to lose some of that. Minus x bar. Lose some of that. Plus 2x bar. And so I move all the atoms to the left and then let it balance out. And so there should be a small change. The advantage of this is there's going to be a small change here. And so this is going to be 1.5 minus x bar. This is going to be 1.5 minus x bar. And this is going to be 2x bar. Okay, now let's redo the calculation. We saw that this is the Kp for this was 4.561 times 10 to the minus 31. .561 times 10 to the minus 31. I typically carry extra digits until the very end, and then I'll try to round it properly. This is going to be the partial pressure of the products over the partial pressure of the reactant. So we're going to have this one. This is going to be 2x squared divided by, okay, this is the same, so it's going to be 1.5 minus 3x. Minus x. I made a mistake there. The 1.5 minus x squared. All right, so let's go ahead and solve for x now. So what I'm going to do is I'm going to take the square root of both sides. Probably be the easiest thing. The math on this one's not too bad. Oops. Try that again. .561 times 10 to the 31 minus, take the square root of that. Okay, that's going to be times 1.5. So I'm going to get 1.01303 minus 6. Oh, actually, what am I doing there? .561 times 10 to the minus 31 x is equal to 2x. So I'll just do, I'll just add 4.561 times 10 to the minus 31 to both sides. So this is going to be 2 plus 4.561 times 10 to the minus 31. Okay, and then invert that and multiply by 101,303. Did anybody get x?
No, 5.06 times 10 to the negative 16. I'm not sure that's right.
Okay, 5.06 times 10 to the negative 16. All right. think I had a problem with my calculator here. 5.06515. 475. Oh, we'll just do 5.06 times 10 to the negative 16.
Yeah.
All right. So we're going to do the subtraction here. This change, do you see this change is extremely small? The change. And so how much of the nitrogen did we lose? Well, that's going to be 1.5 minus. Did anybody else get this number here? 5.06 times 10 to the negative 16? Okay. That change is extremely small, so I'm going to write it in decimal form. I'm going to have 15 zeros, so I'm going to go 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then a 506 on the end. And so this is going to give me 1.499. Okay, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 4, 9, 4. Was the change very significant? So we started off with 1.5 bar, and we end up with 1.4999999999999, etc. 494 bar. Was that change very significant? No, and so the change, I mean, we've got to round this anyway. The change is going to come out to about 1.5 bar, according to the sig figs that we have, if we have that. And so what we call this is, we call this a negligible change. Negligible change here. And so, you know what, I'm not going to bother doing the calculation over here. I'm just going to say 1.5 minus this tiny, tiny number is going to come out to about, what? 1.5 bar. So I'm not even going to bother. I mean, it's the same calculation, but I'm not going to bother writing this out. This is going to be 1.5. And even if I round this to like 10 sig figs, it's still going to be 1.5, right? How about this? Was this a negligible change? This was not a negligible change over here. This was a significant change because we started with 0. If we start off with 0 and we end up with 2x, then that's significant. And so over here, this is significant. You know. And that's going to be 2 times this, so I'm going to just write 10.12 times 10 to the minus 16. Even though this is such a small number, this is tiny, but significant. Because we started with nothing, because we started with 0. Zero here. All right, let's double check the calculation here. I always do the double check. So if it comes out wrong, then I'll start looking for what happened. And so I need to take this 10.12 times 10 to the minus 16 and square that. And then I'm going to divide this by 1.5 and square that. Or I can plug in this long number, but if I plug in that long number, it's not going to make much difference, do you think? 1.499. No, it's barely going to make any difference at all. And so I'll do 10.12 times 10 to the negative 16 divided by 1.5. And I'm going to square the whole thing. And then square my answer. And so I get a K value of 4.551 times 10 to the negative 31. Then I compare that to what the K value should be. Oh, it should be 4.561. I'm off a little bit here.
On my calculator, about 4.560.
You got 4.560? All right. I must have. It's hard for me to key this. What, did anybody else get that? 4.560? All right. I need my other calculator. So this matches. It matches the given K. And so that looks like our calculation went okay. So here we don't have to worry about round-off error. You know, there's no problem. Okay, so resetting the calculation. I mean, resetting the initial conditions isn't often. It's a useful trick, you know, to avoid 100% change. There is another useful trick to do. And another useful trick, if we expect negligible change. So if we go back to this N2 gas and O2 gas in equilibrium with 2NO gas, one of the first things we notice is how small this K value is. This K, or Kp, is 4.56 times 10 to the negative 31. And it depends on which direction the change is. If the change is forward, we call it negligible. We call it negligible because we don't expect much product. I mean, 10 to the minus 31. If the change is reverse, then it's significant. In fact, it should be huge. So if we're expecting negligible change, that is, if we're going in the forward direction, the change should be small. And so with our reset initial conditions, we're going in the forward direction. We had 1.5 bar and 1.5 bar. And then over at the NO, we had 0 bar. And then our change is going to be minus x bar, plus 2x bar. As we got to make a little bit of product to get this ratio here. And so at equilibrium, I expect to lose a little bit of the nitrogen, and I expect to lose a little bit of the oxygen. And I expect to gain some product, 2x bars worth, which is significant. I should say negligible change. Anyway, so what we do is this. We set up our K, which is just going to be 2x quantity squared. And then we have 1.5 minus x quantity squared. And then we do something called the simplifying assumption, SA. And that's the trick that I'm talking about over here. It's the simplifying assumption. Or SA. What the SA does is it says that I expect x to be so small compared to 1.5. So what we're going to do is we're going to assume, I don't know what x is, but I'm just going to make the assumption that x is much, much smaller than 1.5. If x is much, much smaller than 1.5, then I have this. 1.5 minus x will just be about 1.5. And therefore, 1.5 minus x is just going to be about equal to 1.5. And then you see the math is a lot easier to solve. And so let's go ahead and solve the math now. SA stands for simplifying assumption. SA. So here, the math is much easier to solve. It's just 4x. Actually, let's go ahead and solve it. The previous one was a bit more difficult to solve. This one is just 4x squared over 1.5 squared. And so let's go ahead and solve that. This is equal to, what was it equal to? 4.56 times 10 to the minus 31. (4.56) times 10 to the minus 31 times 1.5 squared divided by 4 equals, and then take the square root of that. And I get an x equal to 5.0645 times 10 to the minus 16. What was the x that we got previously? Oh, we got the same x. Do you see that? 5.06 times 10 to the minus 16. 5.06 times 10 to the minus 16. Did it make any difference? Really? Actually, I should have written this more digits out. You'd see that it made no difference. We would get pretty much the same answer. And so we got the same answer. Now, this one worked especially well because the change was exceptionally small, but if the change is more significant, then we have to worry. And so we're going to justify our simplifying assumption. Now, the justification is a little bit of a circular argument here. And so we must justify the SA, simplifying assumption. And so what we're going to do is we're going to calculate the percent change. Calculate percent change based on x here. And so the percent change is going to be equal to, in this case, the x is the change. Actually, let me do this differently. On x calculated using assumption. So the percent change is going to equal the change. The change is either going to be x, 2x, 3x, whatever, divided by the initial. So in our case, the change was x, and the initial was 1.5. And then we just convert that to percentage times 100%. So it's going to be 5.0645 times 10 to the minus 16 divided by 1.5 times 100%. Divided by 1.5 times 100. And I get a percent change of 3.37 times 10 to the minus 14%. Now there's going to be a cutoff for this, and the cutoff is totally arbitrary. You know, our cutoff for the simplifying assumption is if the percent change is less than 5%, then we'll go with it. Then it's okay. In this case, the percent change was way less than 5%. And so the simplifying assumption was very valid. But the closer we get to 5%, the greater the error we're going to have. So 5% is kind of an arbitrary value, and it's kind of high. That's a pretty big mistake. And so there's going to be an error in the calculation. But sometimes the math is just too hard. Sometimes the math is so difficult that if you don't do this, you might not get a decent answer. So this is a bit of a compromise here, but the closer we get to 5, the more I'd start to hesitate to use this. Now what if we were at 5.5, you know, or 5.4? If we're at 5.4%, you know, even 5% is a little extreme. So going over 5 is getting too extreme. So eventually we have to cut the line, and the line was cut at 5%. So if you're over 5%, then you probably shouldn't use the simplifying assumption. Try to figure out some other trick to use. And the final fallback is, you know, if these tricks don't help simplify the math and the math is too difficult, what we end up doing is we just do the method of successive approximations. That's the final fallback. So let's take a look at a particular problem. Let's look at number 90 here. A solution is prepared having these initial concentrations. The iron 3 and the mercury 1 are at half a molar to 4 sig figs. The iron 2 and the mercury 2 are at 0.03 molar to 4 sig figs. The following reaction occurs among ions at 25 degrees C. So this is our Kc at 25 degrees C. I need to check one thing. What if what if we wanted our Kc at a different temperature? Is that possible to determine? Yeah, I mean, we went through the equations there, but I forgot to give you one other equation. One other equation is a simple equation to calculate Ks at different temperatures. It's kind of like the Clausius-Clapeyron equation, you know. Maybe I'll talk about that later. But we're given the K value here already, 9.14 times 10 minus 6, which tells me this is biased towards what? The product or the reactant? The reactant. So well, this is asking what will the ion concentrations be at equilibrium. So let's go ahead and set this one up here. So iron 3, 2 iron 3s and a mercury 1. So this is number 90 in your book. I think I have the 10th or the 11th. What number was this? Again, let me just check. Oh, I have the 10th edition. This was number 89. So this is number 90. So So it depends on which edition. Number 90 of the 11th edition. So I have 2 iron 3s and a mercury 1. This is a redox reaction. And this is going to produce 2 iron 2s and actually what's going to oxidize what? And mercury 2 plus here. Looks right. So let's see what they gave us. It was 0.5 thousand, I think, for the first two. This is molar, 0.5 thousand molar, and 0.03 thousand molar for the last two here. Kc 9.14 times 10 to the minus 6. Okay, Kc here is just going to be the product concentration. So the iron 2 plus, this is going to be squared. There's a mercury 2 plus. This will be squared also. Divided by the iron 3 plus. This will be squared. And the mercury 1. The mercury 1 is to the first power, so we don't square that. Alright, the first thing is, what is the direction of the change? I'm assuming the direction of the change is going to be to the left. But the problem is the numerators to the fourth order and the denominators to the third order. So this is a little bit harder to predict. So I don't know which direction the change is going to be. Is the change going to be to the right or to the left? I'm thinking it's going to be to the left because of the small k value, right? But if you're ever uncertain, in this case it's probably, go ahead and safely assume it. Which direction is the change going to be? Well, we calculate Q in order to determine that and compare it to K. So I'm going to calculate QC, which is going to be 0.03 thousand up here, squared times 0.03 thousand squared. 0.03 thousand squared times 0.03 thousand squared is just going to give me 0.03 thousand to the fourth. And then divided by 0.5 thousand squared and times 0.5 thousand. This is going to give me 0.5 thousand cubed. So I'm going to go 0.03 to the fourth, 0.03 to the fourth, divided by 0.5 cubed, 6.48 times 10 to the minus 6. So actually it's pretty close. Look at that. Surprising, right? And this is because it's hard to tell when the orders for the numerator and denominator are different. So you can't safely assume this is going backwards. It's 6.48, but it's just a slightly, small or slightly big. Yeah. So if Q is smaller than K, then does the reaction go forward or backwards? If Q is less than K, we need to make it bigger. To make it bigger, we need more product or we need more reactant? We need more product. You know, my prediction was wrong. The change is forward. And so I was thinking the change has got to be reversed because this K is so small, but it turned out that the change is actually forward. All right, if the change is forward, then we can fill out the rest of the table. And so the change here is going to be minus what? X or 2x or 3x? It's going to be minus 2x. The mercury is going to be minus x or 2x? Minus x. This is going to be molar. Molar. And then we're going to get plus 2x molar for the iron 2 and plus 2x molar for the mercury 2. And so that at equilibrium, I'm going to have 0.5000 minus 2x molar. And then I'm going to have 0.5000 minus x molar. And then 0.03000 plus 2x molar. And then 0.03000 plus 2x molar. So the math comes out to this. The iron 2, which would be 0.03000 plus 2x. So I'm going to 0.03000 plus 2x. And the mercury 2 is the same. And this is squared, that's squared, so I'm just going to raise this to the fourth. And then the iron 3 is going to be 0.5000 minus 2x. Let me square that. And then we'll have 0.5000 minus x. All right, why don't you try to solve this for me and solve for x? It's set equal to 9.14 times 10 to the minus 6. What did you get for your x? You did the simplifying assumption? You can't do the simplifying assumption here because everything would drop out.
Well, I just took out the x on the bottom.
On the bottom?
Yeah.
All right, so what did you get for your x? That's why.
Yeah, I got negative 0.0144.
All right, so did you double check the equilibrium?
No, I didn't.
So you just did the simplifying assumption for the bottom and not the top.
Yeah.
Okay. You could do that. Partial simplifying assumption. Make it easier. And so that means that this is going to be a negative times a negative will give us positive. So this will be 0.5, and then this will be 288. So 0.5288 molar. And then this is just going to be plus that, and so this is going to be 0.5144 molar, and then this will be plus the 288, which will give us negative. So this is going to be minus 144. So 300 minus 144 will be 0.0156. 0.0156. Molar, and then this is going to be minus 2, so 2 is going to be 288, so this is going to be 0.0088 would be 12 molar.
What if both the polys be the same?
Oh, yeah, then I messed this one up. This is not 144, this is 288. So this one I need to change. So 300 minus 288. This is going to give us 0.0012. And so we'll do 0.0012 to the fourth, divided by 5288 squared. Well, actually, I just need to, before we even do this, well, let's go ahead and finish this since we're on this track. I think I have my calculator. Let me see if I have my calculator.
I don't know.
Okay, what did you get for a K?
7.623 times 10 to the negative 12. It's quite a bit off.
Yeah, and then we compare it. It's supposed to be 9.14 times 10 to the negative 6. Is it even close? It's not even close. And the thing is, before we even get this far, what we need to do is we need to justify the SA, which I didn't do. And so here, you know, before I even got to this point, I would have had to justify the SA. And so what's the bigger change? 2x? You just did the denominator, right? A 2x versus 0.5 or an x versus 0.5? Which one's going to be a bigger change? The 2x. So you do the percent change, the bigger one of the two. And the bigger one is going to be equal to 2x versus an x. And so it's going to be 2x over 0.5 times 100%. And so we have our x here. So that's going to come out to 0.0288 divided by 0.5 times 100%. Oh, you know, did I forget to record this? No, I didn't. So 0.0288 divided by 0.5 times 100% is a 5.76% change. 5.8% change. Is a 5.8% change okay? No. You see, I mean, it's even close to the cutoff, which is 5%, but it's not. It's not justified in this case. And so that's a good thing to try. Try the simplifying assumption. If we did the simplifying assumption for all, then the x drops out and we can't solve for x. So you either got to pick the numerator or you got to pick the denominator to do a partial simplifying assumption. But and so the SA just for the denominator did not work. SA for denominator. If we did the same thing and did the SA just for the numerator, it still is not going to work. Did anybody else solve it for x?
I did the simplifying assumption for the denominator.
Uh-huh.
I got 1.346 times 10 to the negative 3 for x.
Oh. 1.463?
1.346
1.346 times 10
to the negative 3.
times 10 to the negative 3. All right, so we do the same thing. We double check. You did it for the denominator?
Yeah.
Okay, so we'll check the percent change. So here, which is going to be 2x. And so that's going to be 2 times, actually let me write that in decimal form. 2 times 0.001346 divided by 0.5000 times 100%. And so the percent change here comes out to 0.53%. Okay, that's okay. It's okay. Then what we would do is we would solve these and then see. So, the concentration here, I'm going to just go, because this is 4 decimal places, so to keep this, I'm just going to go 0.0013. Although we probably should go more, because then we can get a better K value. So I'll go 2 times 0.001346 equals that, and then we're taking that away from 0.5. And so the concentration for this let's do this. For the second value, the one that Mitchell got is 0.4973. And then we'll go with 0.5 minus 0.001346. And this is going to give us 0.49865, if I did that correctly. And then over here, 0.03 plus that, so this 2. $26.92. 0.032692. And this is the same, so 0.032692. All right, now let's double check the K value here. And so I'm going to take that 0.032692 and raise it to the 4th power. And then I'm going to divide it by this squared, so divided by 0.4973. And then we'll divide it by 0.49865. And this comes out to 9.262 times 10 to the minus 6. This is pretty close versus 9.14 times 10 to the minus 6. So the percent error is not huge there. I mean, it's still kind of significant, but this is okay. I don't know what happened. Maybe the calculation is off. So you reset the denominator because you're saying that the change forward is going to be small. So is that why you did the denominator? The thing is, if the change forward is small, on the one hand, that's good because the initials are bigger. So 0.5 versus 0.03. So the initials are bigger. And so we could do this. But if the initials were the same on both, then, you know, then this change would be small on both here. And so the change would be more significant for the numerator. And so that's good. You reset the denominator instead. And so we got this. And so what is the percent error between these? You know, it would be about 0.12 divided by 9.14. So let's try that. 0.12 divided by 9.14. It's about a 1.3% error in the K values. And so what that did was it greatly simplified the math. Otherwise, the math would have been too horrendous.
For X, I just like one
What calculator do you have? And the Casio solved it? Was that the FX 115?
Yeah.
Wow. The Casio, I didn't realize it could solve fourth order equations. What did you get for your X?
I got 1.2939
Times 10 to the negative 3?
Yeah.
Okay. Oh, that's good. I'll have to remember that. And did you double check the concentrations?
No.
Okay. All right, so what are we going to do for this particular problem? One, you could use a solver. If the Casio allows it, then I guess that's okay because Casio is okay for standardized tests. And so you could use that. But what if you don't have a calculator with a solver? What do we do? And so if we don't have a calculator with a solver, and then we'll compare your answer column to this answer, then the simplifying assumption was close, but let's see if we can get it even closer. And one of the things you could do is, what's another trick you can do here? Reset it. And so let's try resetting this instead. So our initials were 0.5000 for the reactant and 0.03000 for the products. And then I'm going to reset this. Which direction should I reset it? Should I reset it to the left or should I reset it to the right? I look at the K, and the K should tell me which way I should reset it. I should reset it to the right because equilibrium favors the right, or I should reset it to the left because equilibrium favors the left. Which side is favored at equilibrium? The left. And so I'm going to reset it to the left. The reason I'm going to reset it to the left is because I don't want a big change. I want a small change. The smaller the change, the more likely the simplifying assumption is going to work. So this is going to be plus 2y, plus y, minus 2y, minus 2y. This is where y is going to be 0.03000. I look for the limiting reagent. This is stoichiometric, so it's fine. And so I'm going to go to 0 molar here, 0 molar here. And then over here, I'm going to be plus 2y, so that's going to be 0.5300 molar. And then I have to take half of this. Half of this would be 0.015. So this is going to be 0.5150 molar here, half of that. Okay, now whenever I have zeros, the change is always going to be in the direction of the zeros. So the change has got to go to the right. And so this is going to be minus 2x, minus x, plus 2x, plus 2x. And so I'm going to just let it rebalance or re-equilibrate itself. These are all molar. And so at equilibrium, I'm going to have 0.5300 minus 2x, 0.5150 minus x, 2x, and 2x. All right, so I can just plug this in. This is going to be 2x to the fourth on the top. And then down here I'm going to have 0.5300 minus 2x squared. And then 0.5150 minus x over here. Now, since this is favored, 10 to the minus 6 is favored to the reactant side, what I'm going to do is I'm going to make the simplifying assumption here now. I'm going to assume that 2x is small compared to 50.53. So 2x is much smaller than 0.53. The x does not drop out of the numerator, but the x will drop out of the denominator. So I'll say 0.5300 here, squared, and then 0.5150 here. I'll just put the parentheses in there. All right, now let's solve for x. So solving this for x is not going to be too difficult, I think. So I'm going to go 9.14 times 10 to the minus 6 times 0.53 squared times 0.515 equals, and then I'm going to divide it by 2 to the fourth would be 2 times 2 is 4 times 2 is 8 times 2 is 16, so that would be 16 divided by 16, and then I'm going to take the fourth root of that, so I'll just square root it twice. So the x value I calculate, now this is different initial conditions, so this x value I cannot compare to Colin's x value. That's because my initial conditions are different than his initial conditions that he used to calculate it. But what we can do is we can compare the equilibrium concentrations. So here, but before I do that, I need to justify my simplifying assumption. So let's go ahead and try to justify this and see if it's okay. So the bigger percent change was the 2x over the 0.53. So the percent change is going to be 2 times 0.01695 divided by 0.53 times 100%. Ignoring sig figs here. So times 2 divided by 0.53 times 100. The percent change is equal to 6.3%. 6.3% is over the limit. This is greater than 5%. So it's not justified. So we tried every trick. We tried to reset it, and we tried the simplifying assumption. But unfortunately, they didn't work. And so what is left to do? Successive approximations. Now I have two equations I can use for successive approximations. I could use the reset equation here. I can't use the simplifying assumption equation, or I could use the non-reset equation. Which one will be easier? The reset. And so I'm going to use the reset equation for this. And so we're going to try the simplifying assumption here. I'm going to try to write it like this. All right, now what's our first x value? Well, the first x value I have, well, the x I calculated is 0.01695, and so maybe that's a good initial guess, but that's too many digits. So probably what I'm going to do is I'm probably going to just round that to 0.017, you know, and then just see what it comes out to. So this is probably a pretty good guess, 0.017, you know, because I don't want too many digits in there, which means the calculation is going to get too horrendous. And so I'll just do 0.017. I'm going to just square it twice, or raise it to the fourth power. Divided by, I'm going to put this in parentheses, actually 0.53. It's going to be 0.53 minus 0.034. If I double that quantity, and then I'm going to square that in the parentheses of that. And then I'm going to divide it by parentheses 0.515 minus 0.017, those parentheses. And the K comes out to 6.817 times 10 to the negative 7. This is too small. Like. All right, what should I guess next? 0.016? Try. We can do that. But basically, if you're doing homework, this is what you can do. We can have Excel calculate it for us. And so I would just set up an Excel table like this. And you can come up with a way to have Excel do this automatically if you want. But in this cell, I'm going to just type in the formula here. And that is, I'm going to say this is going to equal our x, equal 16x. Okay, x is going to be cell A1. So I'm going to just say this is going to equal 16 times A1. And then I'm going to raise A1 to the fourth power. And then we'll go ahead and divide this by well, actually, let me do this in parentheses. 0.53 minus 2x, so 2 times A1, quantity squared, and actually, I'm going to need one more set of parentheses here. Times parentheses 0.515 minus A1. Okay, so that's my formula I'm going to use. So the first one we did was a 0.17 for our x. And so I'm going to type in the formula here. I'm just going to write equals 16 times, then do A, now it's A2 because I'm on the next row. And this whole thing has to be, well actually this is just going to be to the fourth, divided by parentheses 0.53 minus 2 times A2, those parentheses, square that, times 0.515. Okay, yeah, I am. On the end? Yeah, thanks. I got it now, though. Let's see if this works. Did I set that up right? Yeah.
I think the X value is 0.017, not 0.17.
Okay, I'll fix that. Maybe I screwed up the calculation earlier. Okay, so what I'm going to do is I'm going to just try a bunch of these and then try to get it to converge. So the next one, you said it was 0.016 you wanted to try? I'll try 0.016. 0.016, actually our first one was a little bit too big. It came out to 10.9 times 10 to the minus 6. Now we're a little bit too small at 8.47. I think I made a mistake in my calculation earlier. Let me see. This one came out to 10.9 times 10 to the minus 6, which is not too big. I mean, not too small, it was too big. And now if we do 0.016, it comes out to 8.47. Okay, which is too small. So what do you want to do next?
0.0165.
0.0165? Okay. 9.63, too big. We need 9.14. So give me your next guess. 162? Too small. 163. Oh, almost. We just need some more. We need to get it at 1.4. We need it to round to 9.14, excuse me. So give me another one. It's just a hair too big.
0.01629.
The hair too small.
0.6295.
Okay, we're okay. That's good enough. As long as it rounds to 9.14, we're okay.
Chemistry Goldilocks. That's the word.
Yeah, you're right. You could try to get it to 9.140, you know, but there's easy ways. Like, if we have a pattern, like say Excel can do this quite easily. We could make the next one 0.016294. And then what we could do is we can just have Excel just extend this pattern down. So if we vary the sixth decimal place, this is what we get. And then we can just pick the best one from there if we want to do a series. So Excel can do this quite rapidly. And it looks like the best was actually 16294. Now, if you're doing this on a test, obviously you don't have Excel, but you just do this by hand and just try to narrow it down. But if you're doing it in homework, then we might as well just use it. And so, what did you get, Colin?
It was, I got 1.29.
Oh, okay. Yeah, you have a different X value because I'm using that. And so what we're going to do is now we're going to go ahead and calculate our concentrations at equilibrium. And so now you could calculate your concentrations at equilibrium as well.
I just plug X back into the
Yeah. So I'm going to get my X value and then I'm going to double that. And so over here I'm just going to say 2 times this cell so I don't have to punch it in my calculator. 32,588. 0.032588. So this is equal to X and then 2X is equal to 0.032588. So we'll plug that in here. It's going to be 0.53 minus 0.032588. And I get a concentration of 0.497412. Now the benefit of carrying extra digits is we avoid round-off error in our double check. And so this is why I'm going to carry a lot of extra digits. So we have 0.515 minus x, which is 0.016294. It's going to be 0.498706 molar. And then we have 2x, which we already calculated, 0.032588 molar and 0.032588 molar here. All right, now let's go ahead and double check our K. This is going to be 0.032588 to the fourth, 0.497412 squared, 0.498706. Maybe I screwed it up. 9.121 times 10 to the minus 6. Which is off a bit more than I was expecting, but maybe I did something here. You got 9.14 times 10 to the negative 6. All right, then maybe I screwed it up in my calculation here. 9.14 times 10 to the negative 6. Yeah, that's what it should have come out to. And so we're good. All right, so if we could use the reset and simplifying assumption, then that saves us a lot of time. In this case, it failed, but in a lot of cases, it will work. And it doesn't make much difference. How about yours, Colin?
It's almost exactly.
Okay,
5 seconds.
then you're good. Then your calculator is
This one's the FX 115 ES Plus. Is that why? Is it like a different model?
no. Maybe yours is. When did you purchase yours?
Just like a few weeks ago.
Oh, all right. Maybe they upped the. I'm a little bit surprised they allow that on. Because this one's allowed on standardized tests. So if that's the case, it's okay to use. You're fine. But if that's the case, then I'm going to make the equation harder. So you can't use the equation solver. But for quadratics, we have to solve a lot of quadratics, not in this chapter, but in chapter 16 and chapter 17, it's mostly quadratics. And so if it's just quadratic, then use the calculator. All right, I'm going to stop here, and then let's go back to the computer lab, and we'll take a look at the write-up again, the report.